Hello, this is Dr. Muhammad, and this is another video under Design of Steel Structures according to AISC. And today I'm going to talk about beams part 4, because already we have finished 3 parts of related to beams. And in today's video, the contents are related mainly to shear strength. We're going to study about the shear strength of beams and deflection, beam deflections, and we are going to talk after that design of beams through an example using Z tables. Every item or every topic is going to we are going to work an example after that under each topic of them. Okay, now let's go directly to the first part, which is related to the shear strength, and let's talk more about it. Okay, so first of all, we need to understand some basic concepts of shear stress, or the basic concept of shear stress in general, so that it will give us an idea about what we are going to talk about. First of all, if we have a beam, as you can see here, and this beam is under the application of vertical load, okay, as you can see, and it is simply supported, as you can see here. And if we're going to take a infinitesimal prism that is distant x units from this support, then we are going to find that there is shear stress is going to be developed at this particular point. And if we are going to draw the shear force diagram for this beam, it can be something as you can see here. And the shear stress at this particular point that we are interested in, which is at this point at x from the lift support, we're going to find that this infinitesimal prism is going to be under equilibrium. And as you can see, it is on the neutral axis. This means that there is no flexural stresses. It's only pure shear stresses that is going to be experienced by this infinitesimal prism. And it is under equilibrium, right? So based on that, this under equilibrium, I mean that we have the forces that is going to be developed on the perimeter of this infinitesimal prism is going to maintain it in equilibrium. So from mechanics of materials, okay, the basic or the basics of mechanics of material, we can prove that the shear stress at this infinitesimal prism is going to equal this fraction, which is V times Q over I multiplied by B in the numerator. So first of all, what is the meaning of FV here? This is FV. It's the vertical and horizontal shearing stress at the point of interest. So it is the horizontal and the vertical. In our case, we are having vertical only. There is no horizontal. Okay. And then this V, it is the vertical shear force at the section under consideration. So it is the shear force that is coming, or we can obtain it from the shear force diagram. And then Q, which is the first moment of area, about the neutral axis of the area of the cross section between the point of interest and the top or the bottom of the cross section. So if we are talking about point here, for example, this point, then we're going to have the first moment of area of this area, of this part around the neutral axis, for example. Okay, the area times the distance from the centroid of this small area to the neutral axis. Okay, this is the meaning of Q, which is the first moment of area. And I, it is the moment of inertia. The moment of inertia. The moment of inertia about the neutral axis for the entire cross section. If we're talking about rectangular cross section, so it is going to be B times G cubed over 12. If we have other types, then we are going to calculate the moment of inertia about the neutral axis. And B, it is the width of the cross-section at the point of interest. Okay, if we're talking about this rectangular section, then at any point the width is going to be the same. If we're talking about like I section, for example, then maybe it will be different. And if we are having like non-prismatic section, for example, then the width is going to be different or going to vary. Anyway, we are interested in this I sections. Okay, I section. Okay, so this is the governing equation. This is the, as we said, the shearing stress that is going to be developed at any particular point along this beam. Okay. Now let's go to the shearing stress distribution for a wide flange shape. If we're going to talk about wide flange shape, then we are going to discuss about how the stress is going to be represented on I section, as you can see here. Okay, if we have an I section, as you can see, with width TW and flange thickness T flange, the height of this section is D. Then if we are going to have vertical load on this cross section along its length, which is perpendicular to the whiteboard or the screen, then we are going to have the shear, okay, the shear stress from mechanics of material is going to be something similar to this solid line here, which is like this curvy part, which is ending with the thickness of the flange, and then we are going to find an abrupt change in the shear stress starting from the beginning of the web, and then we're going to find another curvy part between the top and bottom, and then we are going to have an X of symmetry, okay, from both around this neutral axis, so we're going to find it the same. The solid line is the maximum stress that is going to be experienced by the section itself. Okay, and the dotted line, it is the average stress on the web. Okay, it is the average stress on web. So as you can see here, the area under this dashed line is almost equal to the area under the solid line. This is curvy and this is an average. So we are going to have almost the same. Okay, so if we are going to superimpose the actual distribution, okay, on the average stress in the web, which is V over AW. Okay, so this is the average stress, which does not differ much from the maximum web stress. So this is the average stress V over AW. Okay, AW, it is the area of the web itself. Okay, so this is the first thing, that if we're going to make an approximation, this approximation is logic. This approximation is logic. Okay. Another interesting thing that we can see that the stresses or the shear stresses that is going to be carried by the entire section, it is concentrated on the web, right? You're going to find that the flanges, they are carrying very small part, right? If we say this is the area, the solid part that I'm filling now, this is the only part that is going to be carried by the flanges, right? This means that the entire shear stress is going to be, almost all of it is going to be carried by the web, not the flanges. Okay, this means that the web is going to experience, okay, shear yielding before flanges, right? If we have a load and this load is increasing, for example, then we are sure 100% that if we are talking about the same material of the web and the flanges, this means that for the load, for the same load, if the material of the web reaching yield, then it would reach before flange, definitely, because the stresses, as you can see, the stress is much higher in the web compared to the flanges. And this is what I put it here. Clearly the web will completely yield long before the flanges begin to yield, as you can see here, without a doubt, because we are having the maximum shear is experienced by the web, not the flange. Okay, so this is a key concept that we need to keep in our mind. And this is a key concept that is going to justify for us why we are interested in webs, not flanges, whenever we are talking about shear stress. Okay. Yielding of the web represents one of the shear limit states. And this is something that I'm going to explain in a few minutes. Okay. That in the web, we are going to check it for the limit state of shear yielding, okay? Because this is considered to be a failure mode that is expected from the web, okay? That's important. So we are not going to think about, or we are not going to mention or discuss something called the shear yielding of the flange. There's something like this, okay? Okay, now we understood why we are interested in the web, not in the flange. How the stress distribution is going to be on the whole cross-section, how we can approximate the maximum shear stress on the web using this dashed line, which is the average, and how we can understand that we need to consider shear limit state as one of the elements of design, or we are going to consider that shear yielding is one of the failure mode that we need to consider in the design of beams. Okay, so this A web, it is the area of the web as I mentioned. Okay, then we are going to think about what is the shear yield stress that we are going to talk about. We know F yield, okay, for the elements, but this is, we can use F yield, this is in tensile, and we are going to, like as we have done with the flexure, we are going to use it as the main element or parameter for checking the upper limits for flexure, for example, and tensile and so on. Tensile stresses, I mean. But for shear yield stress, we are going to consider it as 60% of the tensile yield stress. So our shear yield stress, the yielding in case of shear, it is going to be 60% of the tensile yield stress. This means that the material, steel in general, in tension, it is much better than shear, right? Because the limit here is 60% of the tensile yield stress. We can write the equation for the stress in the web at failure, because we are talking, as I said, we're talking about the web now. We're not going to mention about flange from now on. And failure here means shear failure. There are other types of failure modes. I'm going to talk about it, okay, whether elastic buckling, elastic shear buckling, or inelastic shear buckling. But now I'm talking about the most dominant and common failure mode for hot rolled sections, okay, which is going to be FV. It is the shearing stress is going to equal the nominal shear strength over the area of the web. AW is the area of the web, and it equals to 0.6 F yield, 0.6 F yield. Okay, so this is the shear yielding stress, okay, here on the right hand side. Okay, where AW, it is the area of the web, and the nominal shear strength corresponding to this limit state. This limit states means what? Shear yielding. Okay, I'm talking about shear yielding now. So it is going to be the nominal shear strength Vn, which is nominal here, equals to 0.6 F yield times area of the web. Okay, area of the web. And this is we're going to give it equation number, which is 5.8. 5.8. Okay, I hope that you can understand up till now two things, or to like keep in your mind that we are talking about web. We're talking about the shear yield stress to be much less than the tensile yield stress, is going to be 0.6 of it. And now we obtain the nominal shear strength, which is going to be 0.6 F yield times the web area. So we are going to neglect totally the flanges. They are not going to work for us. We are going to say that our section, if we're talking about I section, hot rolled I sections, okay, not blade girders, it is something different, then we are going to say that this is the nominal strength of the entire shape is the nominal strength of the web. Okay, now let's go to another slide, which is giving some justification for what I've mentioned before, and giving us something important related to the equation that I have mentioned, or from the basics of mechanics of material. Shear stress equal to V times Q over I times B. As I said, take care of this B. Okay, take care of this B. This equation is only derived for thin cross sections. It's not for wide cross sections. Okay, so this equation, which is 5.7 in the textbook, equation 5.7 is based on the assumption that the stress is constant. This is number one. We're talking about constant stress along the web length across the width B. Okay, so it is constant across the width B. So this is the web, and this is the width that we're talking about. Here it is T web, but in this equation, if we're going to think about it as B, and it is therefore accurate only for exactly. This is a key word. This is key word. Small values of B. It is not derived for large values of B. Okay, for a rectangular cross section of depth D and width B, if we are talking about rectangular cross section, for example, and we have here the width B and the depth to be D, based on experiments, we found that this equation is going to be correct. Okay, is going to be correct 100%. Okay, if the width is very small, and there are some errors is going to be there if B over D is exceeding certain limits. For example, if we have B over D, if we have D over B, okay, the depth over the width, okay, equals to 2, then we found that the error is going to be approximately 3%. Error in what? And the calculation of the shear stress. Okay, and we found that if D over B, for example, equals to 1, we're going to find that the error is going to be 12%. And if D over B equals to 1/4, then we found the error equals to 100%. Can you imagine? So we are dealing with an equation that is taking into consideration the thickness of the cross section to be determinant in terms of the accuracy of this equation. Okay, so this is based on some like researchers or some studies, as we can see here. For this reason, equation 5.7, this equation cannot be applied to the flange. That's important issue. So if I'm going to ask you why we cannot apply this equation for the flange, why that we cannot, like, say this B, we can put it instead of the width of the web, it is going to be the width of the flange. So the answer is, based on the studies, we're going to find that this equation cannot be applied because we are going to find D over B, the depth of the flange, which is this depth, over the width of the flange, it is going to be much more than, less than 1/4. This means that the equation is going to be totally wrong. Okay, cannot be applied to the flange of a wide shape in the same manner as for the web. So this equation is only for web. So let's clear everything. So this equation only for whips, okay, for wide flange or for I sections. I'm talking about hot rolled sections now, okay. So I'm not talking about built-up sections or plate girders. It's totally different story, okay. We need only to focus on the hot rolled one, okay. So this is an important issue you need to keep in your mind. Okay, let's jump to the next slide, which is related to AISC specification requirements for shear. Now we have understood what is the meaning of the shear stress concept and how we are dealing with the wide flanges or I sections in general, the importance of the whips, and how we can distribute the shear and how we can obtain the nominal shear strength for our section. Now it is the time for looking to our specification and think about how we can deal with this from the LRFD point of view or ASD point of view. So from LRFD, the relationship between required and available. This is what we call it, required and available. Available, it's the design strength, okay? Available strength means that the design strength. Required, which is coming from the ultimate loading, which is 1.2 dead, for example, plus 1.6 life, okay? So in this case, we need, as we know, as we have done flexural and compression, everything, V ultimate should be less than or equal to phi V, which is the resistance factor for shear. Now we're talking about shear, so it is going to be different than flexure. And Vn already we have explained about it a few minutes ago. Okay, so this is how we deal with LRFD, okay, or the AISC specification requirement for load and resistance factor design. Okay, and we know, of course, V ultimate maximum shear based on the controlling combination of factor load, as I said here, and phi V or phi V, it is resistance factor for shear. We are going to take we're going to talk about this resistance factor based on some cases, so we are going to consider them later. So this is for LRFD. For ASD, the relationship is going to be the same, similar, but we're going to talk about this VA as the maximum shear based on controlling load combination, but here we are talking about service load. Here we're talking about factor load or ultimate load. Okay, and omega V, it is the safety factor for shear. We sometimes take it 1.5 or 1.67, it depends. Okay, so this is how AISC is dealing with the shear story. Okay, and based on AISC equation G2-1, please stop the video, go to the manual specification. This is in the specification chapter G, section 2-1, and look to this equation. Now, you're going to find that the specification is providing for us the nominal shear strength, as we have explained before, very similar to what we have said before. 0.6 a field, already we understood this. This is the shear yield stress. AW, it is the web area, not the total section area, not the flange area. Okay, we understood this part, yield times area. It gives for us force. That's it. But what is this? What is CV here? Why we are taking this CV into consideration? Simply, the CV is going to consider for the failure mode. So CV is taking into consideration the failure mode that is going to be there. Okay, failure mode means what? We have three different types of failure modes, okay, which are, as I have put them here. We have something called web, shear yielding, or web, inelastic buckling, or web elastic buckling. Three different levels. It sounds similar to what we have explained before for the case of flexure, right? That's right. We are having three different types of mode failures, okay, or three different failure modes. Okay, so the first one is the shear yielding. Shear yielding means that the material itself is going to yield, or the web itself, if we say this is the web, so the material of the web itself will yield, means that it would reach 0.6 F yield, and then you're going to find that the material yields here. Okay, and we can put a relation, for example, between H over T web, which is the height of the cross section or the height of the web, and over T web, the thickness of the web, versus Vn, which is the nominal shear strength. And we are going to find that there is two limits here, similar to the flexural case. The first part here is going to give us what we call it web shear yielding. If H over T web is less than a limiting value here, okay, the plastic limit, for example, then our web is going to fail by shear yielding. However, if the value of the H over T web, the slenderness of the web, is larger than this specific limit, and it lies here in the second part here, this is what we call it web inelastic buckling. Okay, web inelastic buckling. And the meaning of web inelastic buckling, we are talking about shear. It is due to shear. So we are going to find like local buckling would take place, whether inelastically or elastically. It depends on another limit here. Here it is going to be elastic buckling. Here it is going to be inelastic buckling. Okay, so the web is going to, for example, it is going to make something like this. If the web is going to, the outer part is going to be yielding, or is going to be under yielding, and the inner part is going to be less cross section, then it is going to be like yielding and buckling. So we call it inelastic buckling because there are some parts of the material is going to yield. But if the entire cross section is going to, of the web is going to buckle, for example, this means that it is elastic buckling without any yielding of the material. Here shear yielding, okay? Shear yielding, 0.6 F yield. Okay, so these are the three things. Well, let's go back again. In our equation, we have CV. So if I ask you what is the role of CV in the nominal shear strength equation in AISC equation G2-1, then you should explain to me this. Okay, the value of CV depends on whether the limit state is related to shear yielding, inelastic buckling, or elastic buckling. Okay, you understand? Okay, for the special case, now we have some special cases. Okay, for the special case of hot rolled I shapes, so we are talking about hot rolled, it's not blade girders, okay, not built up sections, okay, and not cold formed, okay, and we're talking about I shapes, not channels, for example, not HSS, okay, we're talking about I shapes. So there are like two conditions here. So with limitation of H over T web, if it's less than or equal to 2.24 radical of E over F yield, in this case our CV, okay, this is going to give us what we call it shear yielding, which is case failure mode number 1, web shear yielding. Okay, we're expecting it to be in this part. Okay, the limit state is shear yielding, and CV is going to be 1. So this equation, we're going to have put this CV 1. So as if that we are not, there is no other kind of buckling would happen. CV is taking into consideration this, because CV, the definition of CV in itself, it is the ratio of what? Of critical web stress. So if we say like V critical, for example, okay, or yes, V critical over like the V nominal that we are talking about. Okay, so the critical means what is the critical web stress that is going to be there over the nominal one, and the ratio of the critical web stress to the shear yield stress, or the shear yield. In this case, it is going to be 0.6 F field. Okay, so that's what we are dealing with. Okay, in this case, for hot rolled shapes and with under this limit, so we are like having this limit here. This is the limit that we are talking about. Then we are going to find that shear yielding will take place. CV is going to be 1. Phi V is going to be 1 as well. And omega V is going to be 1.5. Okay, so this is for Phi V resistance factor. It's for LRFD. Okay, and for omega V, it is going to be for ASD, of course. So we're going to have it 1.5. Okay, again, and again. So remember, hot rolled I shapes with this kind of limitation, with this special case, okay, which is H over T web less than or equal to 2.24 the radical of E over F field. Okay. Fortunately, most wide flange shapes with F field less than or equal to 50 KSI fall into this category. Okay, fall into this category. So we are happy with this because most of our like problems and examples were falling into this category. Okay, so we are going to use CV to be 1, and then our VN is going to be only 0.6 F field times area width. Okay. Now let's go to the other types. Now we were talking about, remember here, we're talking about what? Hot rolled I shapes. Now what about others? For doubly or singly symmetric shapes, for doubly or singly symmetric shapes, except for round HSS, okay, hollow structure sections, okay, this is, you can find it in G6. We're going to find phi V to be 0.9 and omega V is going to be 1.67. Okay, and we are going to determine CV based on H over T web, the height of the web over the width of the web. So we have like 3 different values here. In this case, we have like one limit here and another limit here. It seems that 1.1 kV times E over F field under the radical, this is the first limit here, which is limit 1, and let's assume this is limit 2. So this is as if we're talking about limit 1 here. If it's less than limit 1 H over T web, less than limit 1, means that we're in the green area here. So this means that no web instability. So we're expecting what? Shear yielding. There is no web instability here. Okay. However, if we are in this this part, the middle part, or this part, we are going to have a kind of buckling. So we are going to have web buckling. Okay, web buckling. If it is less than this limit, which is limit number 2, which is this limit, this value, 1.37 square root of kV times E over F field, then if it's less than it and larger than 1, then we are talking about inelastic web buckling can occur. Inelastic web buckling can occur in this case. Okay, and based on this case, which is the middle part here, CV is going to be calculated as 1.1 the radical of kVE over F field over H over T web. Okay, the third case, without thinking too much, if we are exceeding limit 2, this is the limit here, which is this limit, or this limit, which is limit 2. H over T web larger than this limit. So the limit state is elastic web buckling. We are here. So it is, we are in this cyan part, that is, it is elastic web buckling. And CV in this case is going to be 1.5 1 E kV over H web over H over T web to the power 2 times F field. You're going to find kV here, kV taken as 5. Okay, and you can find these equations for CV you are going to find them in the equation in chapter G of the specification, G2-3-4-5. Okay, so we have like CV here, and you can tell that here CV, it is 1. It is similar to the case of exactly of the hot rolled shapes. It is 1 also. Why? Because we are here. We are in the first part. This is shear yielding. No instability issues here. So we are going to have CV to be the same. But the only problem is not the problem, but the only thing, we are going to have phi v for LRFD or omega v for ASD. It is going to be different than hot rolled. This is for hot rolled, it was 1, and this was 1.5, right? Why? Because we have singly or doubly symmetric shapes. Okay, it is not I section. We said that for I section, hot rolled I shapes, it is having this specific case. Okay, I hope that we have an idea now of what we are talking about. Okay, and now we are like ready to go through the remaining part for understanding the shear strength. So we already have understood now everything. Okay, so we can put our we can also put it in this form or this graph. If we're going to draw a relation between H over T whip versus Vn, the nominal shear strength, then we're going to have the cap here is going to be 0.6 F yield area whip. This is the shear yielding. Okay. And on the horizontal, we are going to put 3 different parts with 2 main limits. The first one is the limit that is distinguishing between shear yielding and inelastic shear buckling or inelastic buckling, whip buckling. And the other limit, which is limit number 2, we said that this is limit number 1 and this is limit number 2, 1.37, the radical. This would give us the elastic buckling, right? So in this area, our shear strength is going to be 0.6 F yield area whip times what is inside the parentheses here. And for the elastic buckling, it is the same, but also we are going to have something inside the parentheses different than here. Both of them, they are function of F yield and H over T whip and the Young's modulus and KV. They are only different in 1.5 and 1.1 here. Okay, so this means that we are going to have elastic buckling in this part. Can also be written in terms of stress, which is instead of having strength, we can use stress, which is everything is going to be divided by the area whip. If we're talking about ASD, for example, so VA, this is the actual strength over the area whip, would give us the applied shear stress, or this is the applied shear on the cross section. Then this one is going to be the applied shear stress, and FV is going to be the allowable shear stress, which is Vn over omega V over area whip. Okay, so we are going to take care of the this letter. This is lowercase, this is uppercase. Always we need this FV should be always less than FV. Take care here. FV, it is stress also. Still, it is stress. And this one is stress also, but this is applied stress and this is allowable stress. Taking into consideration everything. V nominal strength, 0.6 F field area whip times CV, based on which kind of CV that we're going to use, which value, and omega V, it is going to be 1.67, for example. And this is the area whip, always going to be there. Okay, for the most common case of hot rolled I shapes, we are placing emphasis on this because it is the most commonly used for us. So with H over T whip less than, which means that we are here. Okay, we are here. Okay. Again, not here, not this limit. Okay, take care. This limit is different than this limit because here for hot rolled I shapes, this is for the singly and doubly symmetric shapes. So I'm talking about hot rolled shape, the specific case. So FV, which is the allowable shear stress, is going to be directly for CV, it is going to be 1. Okay, area web cancels with this, so 0.6 times F yield over 1.5 gives us 0.4 F yield. Commonly that we are going to use this. So whenever that for hot rolled, without thinking too much, 0.4 F yield is your allowable shear stress. Do not think too much about this. Okay, you need to be to be quick in the calculation. So if your case is hot rolled I shapes, 0.4 F yield, it is the shear strength, shear yield. I mean the allowable shear stress. And the last hint here is that shear is rarely a problem in rolled steel beams, and this is fact. This is a fact. The usual practice is to design a beam for flexure first, and then check it for shear. This is how it works for us. This is how it works for us. That we need to check flexure. This is the important thing, and then we are going to check shear or deflection, as we're going to see shortly. Okay, now we are ready to have an example. Let's go and have the example regarding shear. Okay, you are going to find it in the textbook, example 5.7. Check the beam example. In example 5.6 already we have, like, maybe we have taken this before. So the first thing is, if we have I section, it was an I section, okay, and the cross section, it was wide flange 14, and its weight is 90 kips per foot. So we are having this cross section. We are going to go directly to dimensions and properties table. So please stop the video and bring your manual and check the following value, which is H. We want to get H over T web. This is part 1 of the manual. The web width thickness ratio for this cross section is going to be 25.9. Why we are calculating this? Because we want to check it is whether it is the ideal case for us. We are having hot rolled I section, so we need to check the limit in order to check the shear strength. Okay, so our limit is 2.24 times the radical E over F yield. So E, it is constant for the steel. F yield, because we know it already from the previous example, F yield is going to be 50. If we substitute, we're going to find that it is 54. So the limit is 54. Our H over T web equals to 25.9. It is much less than 54. So this means that our section is going to have shear yielding failure mode. Shear yielding failure mode. So our H over T web, it is less than 2.24 the radical. So this means that the strength is governed by shear yielding of the web. Again, we're talking about the web. There is no flanges here. Okay, and CV in this case is going to be 1, right? Okay, as pointed out in the specification user note, this will be the case for most wide flange shapes with F yield less than 50. So it is going to be the case for most wide flange or wide shapes with F yield less than or equal to 50. Based on that, the nominal shear strength is going to be 0.6 F yield area web CV. It is 1 in our case, because we are in the specific case of hot rolled I sections with H over T web less than the limit. So 0.6 times 50 F yield area web, it is from the dimension and properties table times 1, gives to us the nominal shear strength. Okay, nominal shear strength. Okay, for LRFD solution, now we are going to determine the resistance factor. Our resistance factor, without thinking too much, it is going to be 1. Why? Because we are fulfilling this value. Hot rolled, we are hot rolled section. This is number 1. okay, and it is I section, right? So we are phi v equal to 1. And the design shear strength is, in this case, it is going to be phi v times Vn that we have obtained in the previous slide. 1 times 184. Okay, 0.8, it is almost 185 kips. Okay. Then from the example, in the previous example, we were having the ultimate loading. It was, this is like W ultimate distributed load. It was 2.08 kips per foot, and this distance was 45 foot. Okay, and we were like a simply supported case. For a simply supported case, then we need to calculate what is the required shear strength. So the maximum case is going to be at the reaction at this cross section. So we're going to have W ultimate times L over 2. This would give us V ultimate, right? And this is actually what we have it here. So W ultimate, W times L over 2 gives us 46.8 kips, which is less than the design shear strength that we have here. Okay, the design shear strength larger, it is larger than the required ultimate strength, okay, that is coming from the load combination that we are having. Okay, now I think that already we have covered everything related to the shear strength. Let's go now and see about the deflection, which is another part and an important part also. In some cases we need to check deflection. As we said before, for shear strength it is rarely to be the determinant factor, okay? So we need to check flexure first, and then we can check shear, as I'm going to see, or as we are going to see in the design steps. Deflection, it is important for serviceability limit state. It is not for strength limit state. Means that we need to take care of the serviceability and satisfy the minimum code requirements regarding serviceability. Okay, the functionality of, or the function of the element itself should be, or should meet the minimum requirements from the codes. So let's go now and understand about this. Deflection, in addition to being safe, a structure must serviceable. Okay, a serviceable structure is one that performs satisfactorily, not causing any discomfort or perceptions of unsafety for the occupants or users of the structure. So we have two main different limit states here: safety limit state and serviceability limit state. So safety, it is related to the flexural strengths that we were talking about, and shear also, and so on. This is related to the safety of the element. But whenever we are talking about the serviceability of the element, we are going to talk, most commonly, it is going to be related to deformation for the beams. For a beam, being serviceable usually means that the deformation, primarily the vertical sag, which is, if we have the beam here, for example, there is vertical sag, which is the deflection, or deflection must be limited. Excessive deflection is usually an indication of a very flexible beam. That's right. The design or the cross section is very flexible, which can lead to problems with vibrations. So it's not only related to the serviceability, it is related to another limit state if we're talking about vibration. In some cases, we need to take care of the vibrations of the system. If the structure is supporting some equipment, for example, in industrial platforms and something like this, it's a very common case. So we need to take care of the deflection, because it is an indication to the flexibility of the beam, which consequently is going to bring the vibration problem on the table. Okay, so we need to think about this. The deflection itself can cause problems if elements attached to the beam can be damaged by small distortions. And that's right, actually. Whenever that we have some equipments, for example, as I said, or some elements, they are sensitive to any small distortions, then it is going to make problem for the designer. In addition, users of the structure may view large deflection negatively and wrongly, assume that the structure is unsafe. That's right, because they are like the viewers means that the people who are not professional, okay, the occupants, for example, they cannot understand what is the meaning of safety and serviceability and so on. So they are going to say that, well, if there is a great deal of sag or vertical deflection of a beam, this like give them like an alarming or alarm that maybe this element is unsafe, it's going to collapse. Okay, so we need to avoid this. It's a kind of a psychological aspect here for the users. For the common case of a simply supported uniformly loaded beam such as that in this figure, this sag or this vertical deflection can be calculated easily, okay, by standard equations. That is, commonly we use it based on the simple end conditions we have and the distributed load, which is uniform. Then we can obtain the deflection, which is going to be 5/384 times W, which is the distributed load, times L to the power 4/EI. This is very common and very famous equation for simply supported beams. And deflection formulas in general are available. Okay, deflection formula in general is available in the manual under, for example, table 3-23. It gives for us some formula, deflection formulas going to be given for us. For example, if you like go to this page in your manual under beam, diagrams, and formulas, we're going to find that for the simply supported, we are having like simply supported here, simple beam, uniformly distributed load. You're going to find it gives to you like very useful components, which is the moment and the maximum moment, maximum shear, and among them the maximum deflection at the center. At the center here it's given to us as we have explained before. Okay, so you're going to find different cases. If we have different for different loading, for example, as you can see here, then you're going to find it easily. Deflection formulas for a variety of beams and loading conditions can be found in part 3, design of flexural members, okay, of the manual, as you can see it here. So please stop the video and bring your manual and check this table. For more unusual situations, standard analytical methods such as the method of virtual work may be used. If you couldn't find your case in this table or in other similar tables, then you need to resort to the very basic method for obtaining the deflection and quantify the deflection, which is the virtual work for indeterminate structure, for example. Deflection is a serviceability limit state, as we said, not one of strength. So deflections should always be computed with service loads. Yes, and this is the rationale behind why we use service loads. So there is no factored load here. We're not going to use 1.2 dead plus 1.6 live for checking serviceability. This is not right. This is design load combination, okay, that is related to strength design. But if we're talking about serviceability, then we need to use the service loads, which is dead load plus live load, or dead load only, or live load only. Okay, so to take care of this, if we're talking about service loads, we need to take, or we should not use any factors at all. Okay, because this is what the design is different than the serviceability. Serviceability means that what are the actual loads. We need to know what is the actual load that is being applied on the element so that we can obtain the actual deformation. But the design, it is totally different. We are talking about a different story. We are exaggerating, okay, in terms of dead load and live load, and we are going to compare it with the yield or the limit state that we are talking about, which is the strength. Okay, so totally different approach. Okay, the appropriate limit for the maximum deflection. Yes, here we are going to talk about the maximum deflection. If you go to AISC specification, it actually furnished a little guidance other than statement in chapter L. You can find it in chapter L, which is which is designed for serviceability. It says that deflection should not be excessive. So it is like vague sentence, right? But whenever you go for the International Building Code, for example, ICC, okay, you are going to find something similar to this table that is going to be more specific, that is going to give you some specific values. For example, for roof beam and floor beams, I think that this is our case, floor beam. This is the most common case, and it gives you some limitations, whether for maximum live load only and maximum dead load plus live load, maximum dead plus live load. And another case which is maximum snow or wind load deflection. It gives to you. Actually, our case, the most important one is maximum live load. For steel design, it is the maximum live load. Why? Even that dead load is going to be important for us because we are going to overcome maximum deflection coming from the maximum dead load by cambering. Okay, so the only remaining part that we are interested in is the live load deflection. So here, this one is an important limit for us. If we're not going to use cambering for the element or the beam, then we are going to use this limits. Okay, it is based on the length of the beam over specific value, like L over 360 or L over 240, for example. Okay. Okay, the limit states shown in this table, as I mentioned, for deflection due to dead load plus live load do not apply to steel beams. Okay, why? What is the reason? Because we are making, or we have cambering. Okay, so therefore the only what is the meaning of cambering? Actually, it means that we are going to, like, camber is a curvature, okay, in the opposite direction, okay, opposite direction of the load or the dead load deflection. Commonly, the dead load deflection curve is in this direction. So we're going to make cambering. So we're going to make opposite direction cambering or deflection curve, and can be accomplished by bending the beam. We're going to bend the original beam, okay, bending the beam with or without heat. Okay, this is the meaning of cambering. So whenever that we are going to put the dead load, it is going to be straight again, right? That's the point. Okay, that's the point regarding cambering. So this is why, therefore, only the live load deflection is of concern in the completed structure. Okay, especially if we're talking about steel, and also it is based on your specific situation. Okay, do not take it live load only. You need to check whether that the beam or the element already it had cambering or not. Okay, let's go to the next. We are ready, I guess, now for the example. We are ready for an example on this. It is going to be short example because it's deflection is not a big deal actually for us. So the example says compute the dead load and live load deflections for the beam shown in this figure. If the maximum permissible live load deflection is L over 360, it's given for us here. Is the beam satisfactory? So we want to check it, whether the beam is going to be satisfactory or not. Okay. So as we said, this is a steel beam, wide flange 18 by 35, and the length is 30 foot. It is more convenient to express the deflection by inches or in inches than in feet. Okay. So units of inches are used in deflection formula in general. Whenever you go back, you're going to find that inches are going to be used in the tables that I have shown you a few minutes ago. The dead load deflection needs to be calculated in live load. Actually, that dead load is not going to be used here because, as I said, this is steel. So we need to go directly to the live load deflection. This is simply supported. You can go to the table, okay, and you can get the value WL 550. So 5 over 384 WLL to the power 4. It is 30 foot. Take care of the conversion here. And WL, it is 0.55 0 over 12. Take care of the conversion because we're talking about pound per foot. E and I, 29,510 I. From where this I? Dimension and properties table for this cross section. Can get it now. So you are going to find that you are ending up with 0.678 inches. The maximum allowable given for us, L over 360, which L here 30 times 12 for the conversion from foot to inch over 360 gives us 1 inch. This is 0.6, this is 1 inch, then we are okay. The deflection or the beam satisfies the deflection criterion. Okay, so there is no problem with this. Okay, so I think that this example is pretty easy and straightforward. You can do it and you can work by yourself any deflection problem as long as you can calculate it, whether using the tables or the virtual work, and you can check the limit based on the given input or based on International Building Code, as we have mentioned regarding this important table. Okay, now I think that we covered shear strength and deflection of beams. Now let's go to the important part, which is related to the beam design. So we now understood everything related to the flexural strength of the beam, shear strength of the beam, serviceability limit state in terms of deflection of the beam. Then the last thing is beam design steps. We need to know from where we can start and what should we check in our way for the appropriate design. Okay, I'm going to give some hints about how to go through this. Okay, it is typical procedure. We need to always repeat it over and over again until that we are getting familiar with it. Okay, first of all, the design philosophy of beams, as I have mentioned before and have already discussed about it before. Beam design entails the selection of cross-sectional shape that will have enough strength and that will meet serviceability requirement. So whenever that we are designing for the beam, we need to fulfill two things. First thing is the strength requirements. The second one is the serviceability. Okay, serviceability requirements. Strength and serviceability. These are the two things or two limits that you need to meet, or two requirements that you need to meet. As far as strength is concerned, strength here means that flexure strength or shear strength. So the strength here means that flexure, for example, okay, or shear. Okay, so flexure or shear. Serviceability means that deflection. We're talking about deflection here. Flexure is almost always more critical than shear because we have flexure and shear. So flexure is going to be our main concern. We need to check it first. So the usual practice is to design for flexure and then check shear. Okay, and then we're going to check for shear. So this is the design philosophy for us. Okay, first go with the flexure, then check for shear, and then we're going to check for deflection as at the end. Okay, now if we put this design philosophy in our mind, then we're going to find the coming is going to be easy. Let's go with the design steps. This is like some hints, okay, written for you just to remind and refresh your mind regarding the steps, but the steps are going to be understood like more conveniently by working out an example. So let's go with the design steps and keep it in our minds. Keep these hints in our minds. Compute the required moment strength. This is the required. The required means here that comes from the load combination 1.2 dead, for example, plus 1.6 life. Okay, i.e. the factored load moment M ultimate load for LRFD, or the unfactored moment MA for ASD. Okay. We have an issue here, which is the weight of the beam. We do not know the weight because we didn't design the beam yet. So the weight of the beam is part of the dead load, but is unknown at this point. So we are going to assume it. A value may be assumed, and verified after a shape is selected, or the weight may be ignored initially and checked after a shape has been selected. So we have two ways here. Okay. Because the beam weight is usually a small part of the total load, if it is ignored at the beginning of a design problem, the selected shape will usually be satisfactory. This means that we are going to check it at the end when the moment is recomputed. So we can like ignore it, and then we're going to recheck at the end after we've done the shape selection. Okay. Okay. The second step is select a shape that satisfies this strength requirement. We're talking about flexural. Okay. We're talking about flexure now. This can be done in one of two ways. Okay, we have A or B. Assume a shape, so we're going to assume any shape, compute the available strength, which is already provided by this shape, and compare it with the required strength, right? We're going to, commonly we do like this. Revise if necessary. The trial shape can be easily selected in only a limited number of situations, okay? This is actually, you can find this, you can refer to this example in the textbook. Okay. Sometimes you are going to find some limitation regarding the trial shape. So you're going to start with a trial shape that is going to satisfy, or at least going to satisfy some architectural requirement, and you can design or you can check based on this first trial shape. The other case, the other way or other strategy is use the beam design charts. We are going to use this in our example. Beam design charts in part 3 of the manual. This method is preferred. So we prefer this method, okay? We prefer this method. And we explain it in the following example that I'm going to explain. Now, by ending this step, we already have maintained and checked the strength limit state in terms of flexure. Then step 4, check the shear strength as I have explained before, and then at the end we are going to check the deflection. Okay, check the deflection. Okay, I hope that everything is okay and it is clear. I think that it's pretty straightforward now, and I hope that we can continue until that we reach to the end of the example. Okay, now let's go and have our example. Okay, this example, you can find it, example 5-10 in the textbook. The example says, select a standard hot rolled shape. So we are talking about standard hot rolled shape. What does it mean? Especially for the flexure, this means that we need to check something h over t web. If it's less than specific value, then we are talking about CV equal to 1, phi equal to 1 also, right? And for AISD, the omega is going to be 1.5. This automatically should be in your mind. Still, we didn't do anything, and it's not the right thing now, but at least you need to keep the keyword. Whenever you see it, it should resonate with some principles in your mind. A992 steel means that our F yield, directly F yield equal to 50. For the beam shown, whenever the beam shown here, it is simply supported, means that we are having 5 over 384 for the deflection, blah, 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 right? So we have something for the deflection for our case. So this is the meaning of the beam shown. It is simply supported. The beam has continuous lateral support. What is the meaning of continuous here? Lateral support means that lateral torsional buckling is not going to be an issue for us. Okay, lateral torsional buckling is not going to be an issue for us because it is continuous support. No problem. We are not afraid from the flange to buckle elastically or inelastically. Okay, and must support a uniform service load of 4.5 kips per foot. Okay. Only. This is live load. So we have live load. Where is the dead load? It didn't mention anything. So dead load in this case equal to what? 0. It equal to 0. The maximum permissible live load deflection as L over 240. So it gives us the maximum permissible here. It gives us the maximum permissible. Okay, then we are going to design smoothly because everything is given in this example. So let's start with the LRFD solution. Then we're going to start with what we have said and mentioned before. Ignore the beam weight initially, then check for its effect after a selection is made. So we are going to ignore the weight of the beam. And then we're going to calculate the distributed load that we have, the ultimate distributed load. We need it. 1.2 WD, it is 0. And plus 1.6 WL, it is 4.5 given for us. So it gives us 7.2 kips per foot. The required moment strength is going to be, we are talking about simply supported, so we are having the maximum moment to be in the middle. This means that WL squared over 8. This is the maximum moment. We have W ultimate 7.2, we substitute here, and L it is 30 given for us. Then we are going to obtain the value of the moment, take care of the units, 810 foot kips. Okay, this means that the required moment strength is giving, or this is the value that is required to be provided from our section. Okay, so the required equals to required phi b times mn. This should equal to, because we are designing, so we should equate it with phi b times mn. We need to make an assumption that our section, or we need to assume whether that our section is compact or non-compact or slender. Then we are going to just assume it. Assume that the shape will be compact. Okay. Then for a compact shape with full lateral support, from where we got this? Here, continuous lateral support. In this case, we are going to assume our section to be compact. This means that the nominal moment strength is going to be the plastic moment. Do you remember the flexure strength? Plastic moment equals to F field times ZX, ZX. Okay, so this is the shape is assumed compact, so we are talking about plastic moment. And F field times ZX, we want to get ZX here. Okay, so from M ultimate that already we have obtained before, we are going to equate it with phi b times mn, right? And we are going to rearrange. So mn already it has phi f field times zx, phi b times f field times zx larger than M ultimate. Okay, this M ultimate known for us already, 810, right? Then zx, we are going to leave it on the left hand side and put everything in the right hand side. Everything is known for us. M ultimate is known, F field is 50, phi b it is going to be 0.9, or talking about flexure. This gives us ZX. This is what we call it, the required plastic modulus. We are talking about plastic modulus. Okay, it's not elastic modulus. Take care, because we, as I said, it is the shape is compact, so we're talking about plastic modulus. Okay, not SX. Take care. Okay, so this is ZX should be equal to or larger than this value. Then we're going to use ZX table. ZX table in this case. The ZX table lists hot rolled shapes normally used as beams in order of decreasing plastic section modulus. So ZX is going to be decreasing value. Furthermore, they are grouped so that the shape at the top of each group in bold type is the lightest one in terms of its weight, that has enough section modulus to satisfy a required section modulus that falls within the group. What is the meaning of this? I'm going to show to you in the next slide. This is the ZX table. Stop the video, bring your manual, and check this table 3-2 for wide flanges, for example, under F field equal to 50 KSI. This is like titled with selection by ZX. You're going to find this ZX is going to be tabulated. If you look here, you're going to find that it is decreasing. 224, 221, 214, and so on, going down. And you're going to find the shape corresponding to it on the left column. You're going to find that they are grouped, as you can see here. And each group, you're going to find a bold shape at the top of the list. This shape is going to be the lightest cross-section that is providing the highest ZX in the group. Okay, for example, here it is 76. This is the weight. All of them, they are higher, or the remaining are higher than this, but its ZX is 200, which is higher than the others. Maybe it is a little bit counterintuitive. You might ask that how that this the weight is being higher and ZX are going to be less, because actually the distribution of the area, it is not related, the area of the cross section, okay, which means that the weight is not related to ZX directly. Okay, the distribution of the area itself might be different because the flanges area and so on, maybe they are different here, then they are going to make ZX to be different. Okay, so that's important to note. Okay, in this example, the shape, we have 216. The shape that comes closest to meeting the section modulus requirement is wide flange 21 by 93. Let's go here. That's right here. We have 216, right? If you go, this is 200, 211, 212, 14, then we are here between 214 and 221, right? So we are going to use 221, which is W21 by 93. And this is what we have assumed that it is going to satisfy, okay? With ZX equal to 221. But if you look to the table, you're going to find that this group, the lightest is going to be W24 by 84, which is having ZX224. Right? So this means that the lightest one is W24 by 84 with VX224 inch to the power 3, the top of the list in bold. Because the section modulus is not directly proportional to area, this is what I've said already, it is possible to have more section modulus with less area. That's right. Okay, they are not proportional to one another, and hence less weight. So do not think too much about that, how much or how come that the weight is higher but ZX is decreasing, because they are not proportional. Okay, try a W24 by 84. This shape is compact. This shape is compact. So let me ask you why it is compact here. Simply as assumed, because we have assumed it in the beginning, but we want to be sure that this shape is really compact or not. Why? Because if you look to the shape, this shape in the ZX table, the shape has no footnote in the ZX table, so it is compact. If we go here, there is no footnote here, there is nothing here. Okay. For example, for this one, it has F here, so maybe there's something it is going to give shape exceeds compact limit for flexure with 50, a field equal to 50, for example. So this shape is non-compact. However, our shape, there is no footnote here. So the shape, our shape here we're talking about, the shape has no footnote in the ZX table, so it is compact as we have assumed. Okay. But in properties, take care of this. If you go to this shape, which is W24 by 84, for example, check it please. But in properties and dimension table, it has a footnote, says it is slender for compression. Take care. It is slender for compression with F field equal to 50 KSI. Our case now, it is flexure, not compression. So this shape is slender for compression. If we were taking this shape as a column or compression member, then it will be slender. We're not going to use it. But our case, not compression, it is flexure. And here in the ZX table, there is nothing in the footnote, there is nothing related or telling us that it is non-compact, for example. Our case is flexure, not compression. This means that we should not follow the dimension and properties table because it's talking about compression, not flexure. Okay. We are talking here, we are speaking about flexure, not compression. Okay. Take care of the footnote in each table. Okay. The dimension and properties table, it gives us this slender for compression, not flexure. Okay. Okay, the shape is slender for compression. This is what you're going to find in the dimension and properties table, for example. It is written like this. Shape, which is this shape, W24 by 84, shape is slender for compression. For compression, take care, do not be mixed with this, with F field equal to 250. Okay, so now we are sure that it is compact because non-compact shapes are marked as such in the table. Therefore, Mn equals to M plastic as assumed, as we have assumed. Account for the beam weight now. We know the cross section, then we can obtain the beam weight. WD, it is going to be 0.084 because we have 84 kips per foot. So in this case, and before we didn't have any dead load. So 1.2 times the beam weight plus 1.6, 4.5. This is the new ultimate load that we've got, and the M ultimate is going to be very similar to what we have done before, but this is going to be 7.3, right? Before it was something 7.2. Okay, so it is not a big deal, I guess, and you are going to find that everything is okay. So this M ultimate is 821.4 foot kips, and the required section modulus is going to be ZX M ultimate over phi b F field, as we have done before. It is going to be 219 inch to the power 3. Our W24, it has 224 inch to the power 3. Then we are okay. Our design is okay. Now we finish this flexure strength. The answer is yes. Okay, the answer is yes. This is actually the part of the in the ZX table actually. If the section has a footnote, as you can see below in the ZX table, then it is non-compact as it is given here. Shape as it is given here. It's not our case, but only I'm showing it to you so that maybe you can find some footnote is given on with some shapes here. So the shape, if it has F, shape exceeds compact limit for flexure with F field. Look here, for flexure. The word is very important here, for flexure. Okay, now we are going to we can go to the shear strength now. We need to calculate the shear strength. So in our case, V ultimate equal to W ultimate times L over 2 because we are simply supported. So we are going to have the shear strength here. It is 7.3 times 30 over 2, which is 110 kips. From the ZX table, fortunately, it provides the phi V times Vn. Let's go back and see. Look here. This is ZX table, but it provides this phi V times Vn. And you're going to find it 340. It is provided for us. So no need to calculate anything. So in lieu of basing the search on the required section modulus, the design strength phi b mb could be, okay, it is directly proportional. Okay, sorry for this. This is from the previous part that I have discussed. V ultimate, we obtained it already. And from ZX table, phi v times Vn, it is going to be 340 kips, which is much larger than 110 kips. So we are okay in terms of shear strength. Finally, so this is related to shear, right? This is related to shear. The last thing is going to be deflection, right? Finally, we're going to check the deflection. The maximum permissible live load deflection is L over 240. We're talking about live load here, okay? because as we said, dead load is not going to make anything as long as we are having cambering. Okay, even that cambering is not mentioned, but it's understood that dead load is not going to be taken into consideration for the steel beam design. And this L over 240 is given already, so we are going to have the limit to be 1.5 inch. Delta L for simply supported, from the tables we can put it as you can see here, 5 over 384 times WL L to the power 4 over E IX. If we substitute all the things here, all the parameters are known for us, it gives us 1.19 inch. Our maximum is 1.5. It is less than, we are okay. Then our wide flange 24 by 84, it is fulfilling the strength requirement in terms of flexure and shear, and it fulfills the serviceability, okay, limit states in terms of deflection. So this section is okay for us. This section is okay for us. Okay, this brings us to the end of this video. Thank you very much for listening, and I hope that you can. I know that it's a tall and long video, so please stop at every part, stop at different parts, and try to understand more by bringing your manual and practice by yourself. Thank you, and see you next time.